we're going to do 2.2b, the factor theorem today. So by the end of the lesson, you should be able to recognize the factor theorem and the integral zero theorem, and you should be able to use these two theorems to help you to factor polynomials. You should also be able to, by the end of the period, factor polynomials using the grouping technique, which you remember from grade 10 and 11, hopefully. And you should be able to factor polynomials using a new method called the sum and difference of cubes. All right, let's go. So what is the factor theorem? The factor theorem basically says that if x minus b is a factor of p of x, then the remainder must be equal to 0. And that makes a lot of sense because let's take something like the number 12. If 4 is a factor of 12, which we know it is, then when you divide 4 into 12, you should get no remainder because it divides evenly into it. That's the very definition of a factor. So it's the same with polynomials. If this is a factor of our polynomial, the remainder should be 0. X minus b can be a divisor anytime, and your remainder might not be 0. But for it to be a factor, the remainder must equal 0. Okay? And this one just is the case if you have an a coefficient there. That's the one that we are most comfortable using, right? P of b over a. Okay, so the factor theorem allows you to determine the factors of a polynomial without having to do the actual division. So for example, I could ask you, is x minus 3 a factor of this polynomial function? And if I wanted just a yes or no answer, I could stick in p of 3 and see what my remainder is. And of course, if my remainder was 0, I could be confident saying that x minus 3 was a factor of this. Okay, so let's look at some examples. It says determine whether the following binomials are factors of this polynomial here. So if this is a factor, then I know that p of negative 2 is going to equal 0. Well, what is p of negative 2? P of negative 2 is just 2 times negative 2 cubed plus 3 times negative 2 squared minus 3 times negative 2 minus 2. And when I determine that, that's negative 16, that's 12, that's 6 minus 2. So this is 18, minus 2 is 16, minus 16 is 0. P of negative 2 equals 0. So x plus 2 is a factor. Okay, let's do the next one. I'll just do a different color here. So this is B. Okay, x minus 1. So now we're going to figure out P of 1. We want P of 1 to equal 0. Let's check. P of 1 is actually 2 times 1 cubed plus 3 times 1 squared minus 3 times 1 minus 2. All right, so we get 1 cubed is, that's 2 plus 3 minus 3 minus 2. Look at that. Looks like it's 0 again. So P of 1 equals 0, and we can say, so x minus 1 is a factor. Okay, so I'm just going to erase this. Yikes, let me make it a big eraser, and then we'll just, erase this, and we'll do the C. Alright, so C is 2x minus 1, so we know that if we just go back to basics, A equals 2 and B equals 1, so I'm really finding P of 1/2. Remember, P of B over A. That needs to equal 0, so let's see. P of 1/2 is 2 times 1/2 cubed plus 3 times 1/2 squared minus 3 times 1/2 minus 2. All right, so p of 1/2. That's 1/8 times 2, that's 1/4. This is 3/4. This is minus 3/2 and minus 2. Oh, it's not looking good. So this is 4/4, which is 1. 1 minus 2 is minus 1, and minus 1 minus 3/2 looks like it's going to be minus 5/2. Now just double check that. I'm doing that without a calculator, but that's what it looks to be. So this is our conclusion here is, so 2x minus 1, you could just say p of 1/2 does not equal 0, so 2x minus 1 is not a factor. Okay, so that's the factor theorem, and that's really something that we're going to be using a lot. The integral zero theorem. Okay, so this one basically says that if you have a factor of a polynomial such that it's x minus b, where you have a leading coefficient of 1 and where your polynomial has a leading coefficient of 1 and the remaining coefficients of all of the terms are integers, then the b is a factor of the constant term of p of x. All right, what does that mean? Let's see if we can figure this out. So if you want to factor a polynomial, you need to use the integral zero theorem to determine all of the possible factors of the polynomial. So I'm not going to ask you, for instance, is x plus 2 a factor of this? I'm going to ask you to factor this polynomial, and you're going to have to decide which binomials are going to be factors. And the way you do that is by looking at the constant term of the polynomial, if this was a 1, and all of the factors will actually be factors of this number. So in other words, a factor of -2 would be 2 and 1, 2 and -1, -2 and +1, and those would be factors. You see here where we had factors, but this was a 2, so I'm kind of digressing here. But if you have, let's go over it again, a leading coefficient of 1 in your polynomial function, and everything else is an integer, we know that the b is a factor of your constant term of your polynomial. Okay, so what you would do is you would try and figure out all of the factors, and you're going to test them using the remainder theorem to see if they give you a remainder of 0. Once you do that, you're going to divide by that binomial or by that factor that you just found using what you know now, long division or synthetic division, and you're going to repeat that until it's fully factored. So this is how you factor a polynomial using the factor theorem and the integral zero theorem. Okay, so let's just do an example, and that might help. It says factor this. Okay, so we can see that there is a leading coefficient of 1. We can see that all of the other coefficients are integers, and if that's true, the integral zero theorem says that our factors will be a factor of this number. So let's see. I'm going to say that then RA and our B is going to equal a factor of this. So it's going to be plus or minus 1 is a factor of -18. Plus or minus 2 is a factor of -18. Plus or minus 3 is a factor. Plus or minus 6 is a factor. And plus or minus 9. These are all possible factors of this polynomial function. One of these numbers, one or more actually of these numbers, is going to be a factor. So when I say the number is a factor, I really mean the binomial x minus 1 and x plus 1, x minus 2 and x plus 2. Those are going to be factors of this. So we've got b equals plus or minus 1 all the way up. I've written those. So what I need to do now is test. And I'm going to test as many as I have to until I hit upon one that gives me a remainder that's 0. So I'm going to test p. I'm going to try the easy ones first. Let's try p of 1. So 1 to the 4th plus 3 times 1 cubed minus 7 times 1 squared minus 27 times 1 minus 18. All right, when I do the math, 1 plus 3 minus 7 minus 27 minus 18. I can see right away that's never going to be 0. Okay, too many big numbers here that are being subtracted. So 4 minus 7 is minus 3 minus 30 minus 48, looks like. And so we would say, so x minus 1 is not a factor. Remember, you take the opposite sign of the b. Okay, so let's do the next one. Let's try p. Yeah, it might work. P of negative 1. So let's look at that. Negative 1 to the 4th plus 3 times negative 1 cubed minus 7 times negative 1 squared minus 27 times negative 1 minus 18. So when we do this one, we get 1 minus 3 minus 7 plus 27 minus 18. So this is more possible here. So 1 minus 3 minus 2 minus 9 plus 27 is 18, and 18 minus 18. Okay, that one is 0. So right now I know I can conclude x plus 1 is a factor. Okay, so this is good. We have one of our factors. So now what I can do is I can start either my long division or my synthetic division. So let's just do synthetic division. So I'm going to take this. I'm going to take the coefficients are 1, 3, minus 7, minus 27, and minus 18. I'm going to just put a minus and a time sign there. I'm going to come down 1, 2, 2, minus 9, minus 9, minus 18, minus 18. If this doesn't come out to 0, then we've done something wrong, because we know if this remainder is not 0, then we made a boo-boo here, because if it's a factor, the remainder should be 0. And indeed, when I do this, the remainder is 0. So that's good. So now I'm just going to put it all together, and I'm going to say p of x, so far what we know is going to be equal to x minus 1, which was our, x plus 1, which was our factor, times whatever this is. This is our quotient when we divided this, x plus 1, into our polynomial. So our quotient now, this is our constant, this is our x, this is our x squared, this is our x cubed. So x cubed plus 2x squared minus 9x minus 18. All right. Now, at this point, you're going to use everything you know to factor this again, because we have to fully factor it. And we could repeat now, pick another number, use the integral zero theorem to come up with factors again of minus 18, and find another number that substitutes in here to get us 0 for our remainder, and then start the process over. But I'm going to tell you one thing. I'm going to look at other methods because this is very tedious, as you probably can tell. And if you can factor, it doesn't have to be a cubic, it can be a quadratic, and you know how to factor a quadratic without using this method. You can use whatever is in your pocket up till this point. So I am going to say that this can be factored using grouping, because I know that if I group this together, I'm just mathematically, I might get myself into trouble here, because I'm going to, see, this is not true, really, plus 18. When I factor this, I'm going to get, I pull out the common factor of x squared, and we end up with x plus 2, and then this is minus 9 times x minus 2, and when I put this all together, I end up with p of x is equal to x plus 1 times x squared minus 9 times, what did I do here? Should be plus, sorry, times x plus 2. This isn't fully factored still, because this is factorable by difference of squares. So this is x minus 3 times x plus 3 times x plus 2. I don't like what I've written here because technically the math isn't working for me here. Maybe I could put if I put a bracket here, that's going to work. There. And if I put a bracket here, that's going to work. Okay, now I'm happy. All right, fully factored. Can't get any more simple than these linear factors there. So at this point, we'll go back and make sure we answered the question that was asked. It just asked to factor, and so you have factored the polynomial. Okay, so quite tedious to test, and you're going to use, I'm just going to go back over this, you're going to use your common sense here. Sometimes it's if you had, for instance, all even exponents and you had all positive signs, you know that if you put in a number here, you're not going to, if you put in a positive number, you're never going to get 0. Even if you put in a negative number, if they were even and everything was positive, you're never going to get 0. So there are times when you can use logic to shorten what you have to do here, and use the, you can kind of guess as to whether the choice is going to work for you. Okay, but it is generally just a very tedious process to factor these big polynomial functions. Okay, we're going to talk about the rational zero theorem. This is just a version of the integral zero theorem. So integral meaning integer, rational meaning fraction. So if you have a polynomial with integer coefficients and you have an a here, so you've got it's interesting. Suppose is a polynomial function with integer coefficients. So basically, you don't have a leading coefficient that's 1. Your leading coefficient is not 1. Then what you would want to do, it's not really saying anything about the leading coefficient here, but you need to think about that. So p of x has a leading coefficient that's not equal to 1. And if that's true, then the b is a factor of your constant term. That's the last term of your polynomial. And the a that you're going to come up with in your factor is going to be a factor of the leading coefficient. Okay? All right. That's the rational zero theorem. So what has to be different to use the rational zero theorem is really that your leading coefficient is not equal to 1 for your dividend. Okay, let's do an example of that. So here we go. We've got one where we've got a 3, which of course means we can't use the integral zero theorem. We have to use the rational zero theorem. And what this says is that, okay, you have to take all of the factors of your last number. So that's going to give you your b. So your b is going to be plus or minus 1 and plus or minus 2. And your a is going to be factors of the leading coefficient. So plus or minus 1, plus or minus 3. And your actual divide or factor will be b over a. So what you have to do, I should do it here. So what you have to do for b over a is come up with all the combinations of b over a. So if b were plus or minus 1 over plus or minus 1, that would work. Or if b was plus or minus 1 over plus or minus 3. Or if b was plus or minus 2 over plus or minus 1. I'm just writing them out very sort of rudimentary here. And then the last one would be if it was plus or minus 2 over plus or minus 3. So can we write those numbers? This is plus or minus 1. This is plus or minus 1/3. This is plus or minus 2. And this is plus or minus 2/3. So we know that b over a is one of these numbers. And one of them we're going to substitute in to see if we can get 0, because we would know then that that would be a factor. So we're going to find p. Well, so I'm just going to test here. And of course I'm going to test it with the whole numbers because they're easier to work with. And I would go back up and just quickly look at this. Do you think if I put a 1 in there, it's going to work? 3 plus 2 minus 7 plus 2. Hey, I think that works. So p of 1 is equal to 3 times 1 cubed plus 2 times 1 squared minus 7 times 1 plus 2. All right, so that's 3 plus 2 minus 7 plus 2. So this is 0. So p of 1 is equal to 0. So what's that conclusion then? So x minus 1 is a factor of p of x. Okay, we can start with that, right? So that we can divide now our p of x by x minus 1. Again, with the synthetic division, it takes up less room, so I'm just going to do that. So my coefficients are 3, 2, minus 7, and 2. And we're going to do subtraction and multiplication. So bring down the 3. And here we go. Minus 2. 2. When I subtract, I get 0. Okay, I think I might have done that right. Oh, oopsie. All right, so now we have p of x is equal to x minus 1 times, this is 3x squared, 5x minus 2. Plus 5x, I'm sorry, minus 2. Okay, so we're getting there. It's factored, but is it fully factored is the question. Can we factor this even further? And so we go to our other methods that we know for quadratics. So man method, for instance, two numbers that multiply to minus 6 and add to 5, positive 5, are 6 and negative 1. And then this is x plus 6 over x minus 1. So sometimes you have to do some of this sort of in the margins. Bring down the 3, and you would get x plus 2, and then 3x minus 1. So x minus 2, x minus 1 from here, x plus 2, and 3x minus 1. So we'll just fix that for us here. So that's an x minus 1. Okay. So we've got x minus 1 times x plus 2 times 3x minus 1. Just curious, if we go back and look at 3x minus 1, that would mean that our b over a would have been positive 1 over 3. And was that one of our possibilities here for b over a? Here, I'll just write in b over a here. Yeah, 1 over 3, right? So we could be pretty confident of this answer. So we have factored this. Okay. All right. I know that's tough. I know that you really need to practice this. Sorry, I don't know what this is. So we're just going to move on. You're going to get to practice it in your consolidated and your homework, but right now I'm going to start something different here. This is another factoring method. Some people have difficulty understanding this method. You just have to memorize it, really. So if this is a difference of cubes, so you know difference of squares, right? X squared minus a perfect square here would be a difference of squares, and then it would be just x minus a times x plus a if these were both squareds. This is different. These are a difference of cubes, and there is a method for factoring a difference of cubes if you ended up with a polynomial like this. So, excuse me, x cubed minus 8. Well, 8 is a perfect cube. You can write this as x cubed minus 2 cubed. And then to factor it, what you do is you write out x minus 2, so x minus a, where a is the cube root of the number here. And then you're going to just take the first term and square it. You're going to take the two terms and multiply them together and change the sign. No multiplying by 2 here, just multiply this times this. And then you're going to square the last term. And you're done. Okay? That's difference of cubes. Let's try it again. This is a difference of cubes, right? Because this is 5x squared cubed minus 2 cubed. So really, our x is 5x squared, and our a is 2. And because this is a difference of two perfect cubes, I'm going to end up with 5x squared minus 2. And then what I do is I square this, so that's 25x to the 4th. This times this with a different sign, opposite sign, so this is plus 10x squared plus 4, square the last term. Okay? So the cube root of this minus the cube root of this, and then square this, multiply these two together, change the sign, and then square that. Okay, that's the difference of cubes. So you have to memorize that. Sum of cubes is very similar. So this is an example of a sum of two cubes because, of course, there's addition in between. This is a perfect cube, and 64 is a perfect cube. So I could write it like this, x cubed plus 4 cubed. And then we'll just write that as the cube root of each of those, which is x plus 4. And then in this case, you take the square root of this one, the square of that one, which is x squared. This times this with the opposite sign again, so that's minus 4x, and then plus 16, square the last number. Done. Okay, and this is not factorable any further. Neither is this, neither is this. Okay, so there's nothing that you can do to factor it any further. All right, this one looks tough. Let's take the cube root of 512. I'm going to go with 6. Is that right? 36 times... no, maybe not. is it 8? I don't have a calculator in front of me, so I'm just going to do this just to check. Yeah, it's 8. All right, so we're going to write this as 8x cubed plus 4y squared. So the cube root of 64 is 4, because 4 times 4 times 4 is 64. And then y squared, remember, is the cube root of y to the 6th, because if you multiply these three together, you're adding the exponents, right? So this is y to the 6th. So you really just, to get the cube root of an exponent like that, you divide by 3. Okay, so this is 4y, in brackets, 4y squared cubed. Okay, so this is squared here. Okay, so now what we're going to do is factor using the sum of cubes. So you take the cube root, which is in the brackets, 8x plus 4y squared. That's the first thing you do. Then you square the first, 64x squared. You multiply this times this, and that's going to give you 32xy squared with the opposite sign, so that's minus 32x y squared, and the last number is plus 16y, I'm running out of room here, y to the 4th. No, sorry. I don't think I can make that. Move it over. Oy, oy. Sorry. Yeah, I can't do anything about that. Okay, so that's the difference in sum of cubes, and that's something that you will have to memorize, and you may see it on a test, and you may see it in your homework when you're being asked to factor. I mean, these are all just polynomial functions, right? So I can ask you to factor any of these, and you should be able to do it knowing that it is recognizing that it is a sum or a difference of cubes. Okay guys, I know this is tough. This was a heavy lesson. You really do need to factor, or you need to practice fully factoring these polynomials. So get cracking on your homework, please. Thanks.